So 4 hands are up. So anyone can
This
unmute
meeting is
yourself.
being recorded.
All right. Okay, three students have raised the hand. Yes, Deepak, Sanket, and Pradnya. Yes, one by one you can unmute yourself and please tell what do you mean by digital communication?
Transmit data in digital form.
Transmit the data in digital form. Okay, what is the data? In which form is the data available to us?
What, ma'am?
In which form is the data available to us? You said transmission of data in the digital form. Yes. So that we are doing basically with in the like process of digital communication techniques, right? We are processing the digital data, but basically the data is in which form?
Analog.
Yes, analog form. It's a continuous form, and we are going to convert it into discrete form and then finally into our digital part, that is binary, zeros and ones. Sorry, you have already come across like what are the reasons why we go for digital communication. And when we go for digital communication, we have a particular what do you call your processing system or a particular block diagram for your digital communication. Can anybody orally tell me like what does a digital digital communication system block diagram consist of? Just you can tell me the order of the blocks.
Okay, madam has asked the basic blocks of digital communication system.
First, we can transmit the information. Next block is a sampler, which is used to convert the continuous signal into discrete form. Next one is a quantizer, and parallel to serial converter, encoder, channel, decoder, serial to parallel converter, sample and hold circuit.
All right, fine, good. Anybody else would like to say? Yeah, sorry, I was just muted. Yeah. So most of you have come across the digital communication block diagram, and there you have seen what are we doing when we are taking up the source. I mean, we are taking up the information or the input signal, and we are transmitting it to from one point to another point to a particular channel. And when we were transmitting from one end to another end, we have seen that analog signal was being converted to digital part, right? Uh, During that, we came across the transmitter design also, like what are the requirements or what are the circuitry we need, to have a optimum transmitter. Yes, and we saw that once the data is being transmitted from the transmitter to the receiver end, we have some path. Yes, and that path is called as channel. Correct. So we even observe that at the channel there is some noise being occupied, right? So that noise which is being occupied will interfere in our original message signal. Yes, and with that interference, that information is going to go to the receiver end. So the receiver has an important role to play now. It has to identify which is the original message signal, and it has to remove the noise, right? So in this particular chapter, you will be studying or you will be coming across the sessions or the circuitry part or the block diagrams which are completely related to your receiving channel. How are you going to execute the, or identify the correct message signal at the receiver end? So what is the process and all we will be checking. My screen is visible?
Yes, ma'am.
Yes? Anyone? Yeah, okay, fine. So unit 5, your unit title is optimum receiver for digital modulation. So the contents which you are going to look into are the introduction to optimum receiver, integrate and dump receiver, match filter receiver, correlation receiver, and then you're going to come across your synchronization, yes, symbol and frame synchronization and carrier recovery circuits. So students, in today's session, we will be dealing with these 4 topics. Which one? A brief introduction about the optimum receivers, why do we need, and like what does optimum receiver actually consist of, okay, and when it is consisting, it consists of integrator and dump receiver and plus the match filter, and how are we showing that the demodulator circuit what we are having is, the integrator or the match filter or the optimum receiver, any kind of correlation do we have in that or no? We are checking with respect to those aspects in today's session. Okay. So to begin, I will just say that we have, I'll just display the picture, which are the elements of digital communication system. We have already spoken about your source of information, which is basically analog data, right? And that analog data, you are converting it into the binary form with the help of your source encoder, right? And then you are transmitting this information through the channel encoder to the modulator. Yes. So here we are basically talking about the, band pass frequencies or the band pass filters. Okay. Then once, say for example, this is your input signal I of t, I will take. Yes. And this I of t signal is converted into binary bits and it becomes message signal at the end here, M of t. Okay. Or S of t also you can take. There are various notations how we define the what you call signal. And then this message signal is passing through the channel. So this channel can be anything. Okay. So the channel can be anything when I'm saying. So what could be the channels here? Can anyone say what could be the channels? Channel is basically a path through which our information is being delivered or passed. Now, right now, I am talking to you. We are engaging a class. We are communicating, but we have one channel through which we are communicating, and that is through the Zoom meeting, right? But this Zoom meeting is being organized through what? Through internet connection, right? So internet connection is again what? For me
Wireless.
over here, it is yes, wireless. Yes. So one of the channel path can be a wireless channel or it can be a wired channel. Yes. With respect to telephone systems, we can say. And then what else could be the channel? Ma'am, air is the medium, air is the channel. Okay, I agree to it. And what else? Yes, girls?
Optical fiber.
Yes, optical fibers could be the channel or could be the path to transmit the message signal. Girls, I want you to answer. Okay, fine. It could be water medium too. Do you agree to this?
Yes, ma'am.
Yes. So these are all the various paths through which the information has to be transmitted. Yes, to another end, which we call it as a receiver. Right. So when we are doing this kind of work, when we are passing through the channel, there is lot of noise getting inferred. Okay. Not noise, it is noise. Fine. So slightly writing. Okay. So so here what happens as a demodulator or at the receiver end, we have our message signal M of t with us, plus along with this M of t, we have some kind of noise associated with that message signal. So when this noise is associated with the message signal, we see that we are unable to retrieve the complete information. Yes, now it becomes slightly difficult for us to retrieve the information. So to overcome this difficultness, what we do, we try to remove the noise. Yes or no? Yes?
Yes, ma'am.
Yeah. So when we are trying to remove the noise, obviously we are going to use filters. Do you agree? Yeah. So these filters, what we are going to use are being present over here, the demodulator part. Okay, at the demodulator end. So after demodulation, after recognizing our original signals, which we are receiving from the what you call your source encoder or modulator to the transmitter, that we are going to decode again. Okay, and then finally give the user the information, right? So in this chapter, we are going to concentrate on this part. Okay. So, so here the signal processing operations are performed at the receiver to recover the transmitted information. Why? The reason is because when the message signal is being transferred or it is being moved to the receiver end, we have a white Gaussian noise being associated to it. Okay, and that white Gaussian noise is called as additive white Gaussian noise because it is adding up to the channel. Okay, so here a simple block diagram or a model for a what you call additive white Gaussian noise is given over here for the received signal. Okay, so here we have a transmitted signal. Okay, the transmitted signal is designated by S and here is M. M refers to number of message bits. As we are converting our data, okay, our information, our analog signal into the binary sequence. Yes, so say for example, I have a binary sequence 10110000, right? So this is my sequence. Okay, and it is n bit sequence. What do we call it as? We call it as n bit sequence, right? And this n bit, in this n bit, say for example, I am transferring only 4 bits and let that 4 bits be k. Okay, so at a given rate or at a given time from the given sequence, how many bits are transmitted? That is called as bit rate. Yes. Yes or no?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So now here, when I'm saying yum, what it indicates? It indicates the messages. Okay. This is M1, this is M2, this is M3. This all contains information. Ma'am, it is 0. Yes, it is containing some information because we have converted our analog waveform to a digital binary input. Yes. So all these are message signals. Okay, for an n-bit signal and for that n-bit sequence or n-bit signal, we have some information rate, that is number of bits being transferred. So when this entire signal is being transmitted through the channel, we have some noise adding to it. That is why we have the name as additive. Okay. So at the receiver end, when we receive the signal and let the receiver signal or the what is signal received at the receiver end be designated as R of T. So as I told, the noise will be added here to the transmitted signal. We write it as Sm of T plus N of T, where Sm of T is the transmitted signal and N of T is the what? Noise added, right? So here we can see that the power spectral density, okay, is given by, for the additive white Gaussian noise, is given by Sn of f, that is in the frequency domain they have written, it is given as n naught by 2 watts per hertz. And this additive white Gaussian noise power spectral density is carried out at the receiver end at a given time, okay, at a given time interval, okay, or period. Okay, this is tau actually, time delay you can say. So it is same as that what we are giving at the sorry, which is coming at the receiver end. So receiver में आपका जो transmitted signal और channel का noise जो add होके आता है, वही noise आपको receiver के signal में totally मिलेगा. So just we want to say that the spectral density of the white Gaussian noise is equal to the what you call your noise being added at the receiver signal. Okay. Then what are we going to do? So we are supposed to remove this noise. So we are supposed to remove this noise means I'm coming across demodulator, or which is also called as a receiver circuit. Yes. So what does this receiver circuit consist of? Figure 3 shows the block diagram of a receiver circuit. Okay. It consists of two blocks, that is signal demodulator. Okay. It consists of two blocks, that is signal demodulator and a detector. And finally you have the output decision. Okay. Now what is happening in the signal demodulator? In the signal demodulator, actually whenever you receive a signal during the demodulation process, you are going to have two steps, that is detection step and the estimation step. Okay. Now what is this detection type of theory? Okay. What it actually says. Just 1 second, students. Yes. Yeah. Okay. So I was talking about the signal demodulator realization. So how are you going to do that? It is going to follow the principle of detection theory. Okay. Now what is this detection theory? It actually deals with the design and evaluation of decision making processes. Means it is going to decide that whether the observed what you call it is going to observe the received signal. Okay. And it guesses which particular symbol is being transmitted. Okay. Which particular symbol is being transmitted. Okay. According to some set of rules. So here in the detection theory, or what you call realization, we can say that we are going to have a receiver signal. Okay. Or this demodulator observes the received signal in such a way that what kind of symbols has to be detected. Okay. And this detection circuit, or the realization of the demodulator, signal demodulator, is based on two types. That is, it is based on the use of signal correlators, and it is based on the use of match filters. So it means that here in the signal demodulator, we can go for either a match filter. Okay, it is a technique, and signal correlator is also a technique which is going to observe the received signal and guess which particular symbol was transmitted. Okay, which was transmitted means what we have received here. यहाँ पे ट्रांसमीटर क्या इंफॉर्मेशन सेंड कर रहा है, उसके हिसाब से कौन, ये आपके जो सिग्नल में डिमोडुलेटर हैं, दैट इज सिग्नल कोरिलेटर एंड मैच फिल्टर, ये रिसीव सिग्नल को ऑब्जर्व करके आइडेंटिफाई करने की कोशिश करेंगे कि कौन सा बाइनरी सीक्वेंस ट्रांसफर हुआ है. ओके. एंड दिस is nothing but your received signal, and this received signal we are going to declare it in the form of vector input. Okay. as R1, R2, R3 up to Rn. So we have number of message signals that we are going to declare in terms of vector inputs. Okay. Then what is the next step after demodulation? After identifying, okay, we need to estimate it. Okay. And that estimation is called as optimum detector. Okay. What are we doing here basically? In this optimum detector or in the estimation, we are designing and evaluating, okay, the information which is received in the signal in such a way that we are controlling the number of errors. Means simply you can say that this optimum detector, which is following the estimation theory, is designed to minimize the probability of error. So whatever inputs we had, right, whatever message signals or the message bits we received at the receiver end, after identifying that, we are going to check or decide what we have got is correct or no. Okay, we are trying to remove the probability of error. We are trying to maintain the error rate low. So that part is called as estimation. Fine. And then finally it is given at the output. Okay. Fine. So this part is clear till here. Students, please reply.
Yes, ma'am.
So what are we doing initially? See, if you answer, then I can understand that you have understood. I can move to the next part.
Yes, ma'am. Understood.
Yes. Yeah, please tell me, Avishkar. Yeah,
Yes, ma'am.
Avishkar, right? Yeah.
Yes, ma'am.
Can you please tell me from the beginning, like what all part we have studied in this 10-minute session?
Yes, ma'am. So basically, we need to study the optimum receiver. For that purpose, uh, we have cleared our some basic concept in which AWGN, that means adaptive wide Gaussian noise, is added at the receiver end. Some
No, not receiver end, beginning of the receiver signal.
yes, ma'am. And after that, the formula and
The receiver cell consists of the message signal as well as the noise. R of t is equal to Sm of t plus N of t, where Sm of t is the transmitted signal and
N of t is the noise added.
what we did, what was the next step? What was the next step after receiving? After receiving, we
Demodulate.
need
Okay.
to, yes, demodulate the signal. Yes. So
Yes,
to
ma'am.
demodulate
There are
the signal, we have two blocks.
two blocks. One is the signal demodulator and
Same.
another one is detector.
Yes, correct. So basically what we are doing in the signal demodulator, we are following a detection theory, right? So what is the detection theory? We are actually checking or looking, or we are identifying what are the bits that is transmitted. And how are we identifying? By using the signal correlator filter or by using the match filter. Okay.
Yes, ma'am.
All right, students. Yeah. And then can anybody tell me at the detector end what are we trying to do? Optimum detector, what are we going to do then? We are using the detection theory, sorry, estimation theory. And by using the estimation theory, what do we finally design? Can Aishwarya answer for that? Aishwarya. Shiva Shivraj would you like to say? Yes, Shivraj.
We get to know about the errors. So by through this method, errors can be minimized.
Yes, we are going to design what you call a detector in such a way that we have the minimum probability of error. Okay, P of E should be less than 1. Okay, all right. Now let us move to the next part. So, coming to the topic here. Here, first we are going to talk about signal demodulation. So signal demodulation means basically we are trying to remove the noise by using either of the two what you call techniques. That is your signal correlated techniques or by using the match filters. Okay. Actually, these two are slightly dissimilar. Why they are not similar, I will tell you. But later we have to prove that these two are having the same impulse response. And that will be an important question that prove the impulse response of the correlator and match filter are equivalent. Okay. So the important question from this topic will be that particular one. Okay. Then, so here, one of the detection technique which we are using as per your syllabus is the integrator and the dump circuit. Okay. So what is this integrator and the dump circuit? Fine. Here, this is actually the block diagram of your integrator and the dump circuit. All right. So what do you observe here? Can anybody explain looking at the diagram just before I proceed? Anyone quickly?
Integrator circuit using op amp.
Okay, integrator circuit using op amp. Fine. Then what else? Only 2-3 students are answering. What about rest other? We have 100 of students gathered over here. Anybody please?
At the input side, we are used a summer adder block in that signal x of t and white Gaussian Noisian of t is added.
Okay. Fine. Correct. So you people have a like brief idea like what is actually happening over here. So let us study the operation of this particular circuit or this particular block diagram. So we have our message signal x of t. Okay, and this message signal or simply say transmitted signal. It is being corrupted, okay, or it is getting corrupted by the addition of the white Gaussian noise. So these two are added up, then we get a noisy signal. What do we call this? Noisy signal. Noisy signal is given by x of t plus n of t. Okay, so this noisy signal is being transmitted from the, is traveling from transmitter to the receiver now. Okay, so when it comes over here, what noise we assume it? We assume this noise to be the white additive white Gaussian noise, which we have learnt in the previous slide. Correct? Then what happens? Now this circuit from here, from this resistor part, one second. From this resistor to this switch part. Okay, we call this entire circuit as an integrator. Right? We are going to have our message sample. We are going to integrate each message sample. How are we going to integrate? Right. So here at the input of the integrator, we are getting a noisy signal. And we see that this noisy signal is going to travel over a bit interval t. Okay. So bit interval t means what? Bit interval. That is the bit duration. Say for example, I have the message information 101. Okay. And this 101 is traveling at a bit interval means this bit interval, ये 1 पास हुए तक आपका टाइम ड्यूरेशन और आपका इंटरवल कितना लग रहा है, t लग रहा है, t टाइम. Okay, and similarly when 0 is passing, again that time you have the bit information as t. Okay, so we can simply say when each bit is beginning, okay, at the beginning of the each bit interval, this dumb switch is there, right? This dumb switch is closed monetarily, okay, sorry, momentarily. Fine. Why? Because you want to discharge the capacitor completely. Why? At the beginning, if this capacitor is charged, means what will happen? It will carry the information. So we need to discharge at the very beginning of the sequence. Okay, say I have 101, sorry, 1010, and at the beginning means at the start of this particular pulse, what am I doing? I'm going to close this switch so that my capacitor is discharged completely. Okay, so what happens here? What will be the voltage on the capacitor? What will be VC here when the capacitor discharges? What will be the voltage on the capacitor when the capacitor is discharging? We are closing the switch means the current is flowing here, right? Yes, sir. Yes or no? Here.
Yes, ma'am.
The current will be completely discharged. So what will be the voltage on the capacitor at that particular bit interval? It will be 0, obviously. Discharging of the capacitor means what? There is no current. Yes, no current means no voltage. Right?
Yes, ma'am.
So we simply say that the voltage on the capacitor at the beginning of each bit interval is 0. Each bit interval we are talking. This bit interval, this bit interval, this bit interval, this bit interval. It turns out to be 0. Why we are doing such thing? Why? Because this capacitor will not be dependent on the previous bit interval. We are not going to be dependent on the previous bit interval. We are not going to check what इसका value क्या था और तब जाके हम कैपेसिटर को फंक्शन करेंगे. नहीं, हमें उसको हर बिट इंटरवल को 0 मेंटेन करना है. एंड वो काम कैसे होगा? कि डंप स्विच के ऑन ऑफ के कारण होगा. ठीक है, जब भी आपका इंफॉर्मेशन पास हो रहा है. फाइन. एंड देन afterwards what happens is, for that particular bit duration when we are transferring, this dump switch will remain open. Okay, and then the capacitor is going to discharge linearly. Okay, this explanation is given in your textbook, I guess. Then apart from that, what happens at the end of the bit interval? Okay, at the end of the bit interval. So at the end of the bit interval, you see that this switch SW2, okay, is closed so that the second requirement, what we need, is satisfied. Second requirement will, see, one is transferring. One has to transfer from here to here. Okay. So when one is transferring, we are discharging this capacitor so that the one is moved from here to here. Okay. Then this closes up, we get 1 over here. Then next again, when by the time 1 reaches here, means what is the time we are taking? We are taking the time interval t for every bit. So this is going to repeat, this action is going to repeat for every message bits. Okay, this information is going to be this method or this process is going to be repeated for every message bits. And then finally we get the, instead of getting the instantaneous output voltage, we get the we won't get instantaneous voltage, we get the output at the time interval t. Okay, we'll see this diagram, then we will analyze it slightly better, in a better way. You can see here the signal output voltage. Okay, the signal output voltage and the input voltage is given for a bit duration t in these particular two figures. Okay, you can see that for this bit duration, 0 to t, okay, the switch is closed. Means what? The information is being passed. All right. And what happens to the output voltage over 1 bit? We see that for a 1 bit duration, we are sampling the value of the integrator. Okay. And we get the signal output as, instead of getting x0 of t, means first bit, we are getting it as x0 of capital T. Okay. As we are sampling, we are giving in this particular way. And here we are going to introduce the time delay because of this resistor and the capacitor, which is contributing there. Okay. Then here you can see the output signal. This is in terms of x0 of t for a time interval. Okay, say I am passing a data 1101. So here the sampled information what we have, okay, with respect to this one, जहाँ switch से pass होके निकल रहा है, वो वाला information यहाँ पे mentioned. And this is nothing but noise. The noise is sampled in this particular form with the expression N0 of t. Okay, these are the waveforms of the integrator and the dump circuit. Sorry, this I told as switch 1, but it is actually switch 2. So sorry with that. Okay, so we see that this x0 of t, okay, here we have the expression, you can simply say. So at the beginning of the next pulse duration. So next pulse duration means in the next time interval, the previous time interval, what on the previous output what we have, that is your like at the switch 1, here we had transferred, right? Where is that? 1 pulse we transferred. So we get an integrator output here. That's ready. What is going to happen? When this is ready means this switch will open and this switch will close. Yes, ma'am. For every pulse, ये on रहेगा, तो ये off रहेगा. On means it is connected. Okay. Off means it is disconnected. Fine. Once the message bit is passed or transferred from here to here, then it means that this is going to open and this is going to close, so that the next message bit is ready to be transferred. Okay. As soon as the information reaches here, it will close. Okay, and this will be open again, and then again the next bit is transferred. All right. So that is what happening here. The integrator output is nothing but the summation of your transmitted signal over a time interval t, period of 0 to t, you can say. And you have, when you simplify this expression, you get 1 by RC is a constant value, which is the value of your resistor and capacitor. And this resistor and capacitor is causing some time delay, which is later called as tau, or you can say t. So here I apply this integration to x of t as well as n of t. And when I do that, I'm going to have the equation or the expression for the instantaneous signal voltage, okay, and instantaneous noise voltage. So it is still at the sampling point. Okay, it has not crossed switch 2. Fine. Switch 1, it is at the switch 1. Fine. That is why we are saying instantaneous signal voltage and noise voltage. So those instantaneous signal voltage and noise voltage are represented in this particular form. X0 of t plus n of t. Fine. And now we are saying that let this x of t be positive a. Okay, we are telling that some information has been delivered. How will the some information be delivered? When we have a amplitude value displayed. Okay, if we don't have an amplitude value or the voltage displayed, we say that there is no information being delivered. So we replace this x of t as a of t in this particular expression, or here we are replacing x of t as a of t. So we have here, after substituting x of t is equal to a of t, we have 1 by RC is equal to integration of 0 to t for the bit duration t, you can say, or time interval t, a into dt plus n of t. Okay, so here when I simplify this, I'm saying we have a, again we take out as a constant value, then integration of 0 to t dt is given as 1. So we apply the limits 0 and t, then we get here t plus n naught of t, capital T. So this is finally the integrated output. What we have? We have AT divided by tau, where tau value is given as RC. Okay. And then that we have the noise also being sampled at the time interval. So simply you can say that this particular value is related to the sampled values of the output voltage, and n naught of capital T is the sampled values of the noise voltage. And this is occurring at the end of each bit interval. Okay. At the end of each bit interval. I have here 1, here 0, here 1 and 1. Fine. So this is my bit interval. Yes. So at each bit interval I'm talking. So at this end, at this end, at this end, and at this end, I am going to get the value as x naught of t. At the beginning, what it will be? At the beginning, it will be t. But when it is getting sampled, it turns out to be capital T. Okay. So this is your integrated and dumb filter. Fine. Now you're going to study about the optimum receiver. So here I'm saying signal correlators, right? So signal correlators basically consist of your integrator and the dumb circuit only. Okay. Dumb circuit or the dumb switch here means where we are using to, pass the signal, pass the message bits in an on and off mode, for which is basically used for charging and discharging the capacitor. Okay. So this dumb circuit or the integrated circuit is generally known as the correlator circuit. Okay, correlator basically consists of a multiplier and then an integration circuit. Okay, so we are studying a part of it. Now the second part which we are going to study is the optimum receiver. Okay, or you can simply say it is again continuation of that. So here we are going to use a generalized filter to receive the binary coded information or binary coded signal with minimum probability of error. Fine. See in your syllabus, fine, minimum probability of error. So this is the block diagram of an optimum receiver. So if we look back again, you will say, मैम यहाँ पे मतलब इंटीग्रेटेड सर्किट था, उसके बाद हमको आउटपुट मिला v of t. फिर इसमें उसमें क्या डिफरेंस है? ठीक है, वो क्वेश्चन आता है आपके माइंड में. यहाँ पे क्या है, this optimum filter, this filter what we are talking here. This filter can be your simple low pass filter, okay, or it can be a match filter, or it can be a correlator filter or something like that. But what exactly inside the filter we have is your integrator and dump circuit. Okay, so here say you have a signal x of t, and signal x of t is vectored. Okay, it is vectored into x1 of t and x2 of t. Means we are transmitting logic 0 or logic 1. Say for example, if you are transmitting logic 1, I mean during the transmission of symbol 1, you are using logic 1, say for example that. So we can simply say if there is a binary value 1, let that signal be considered as x1 of t, and it is having an amplitude a. Okay, for a bit period of t seconds. Fine. Say for example, if the binary information is 0, okay, that time you are passing a signal x2 of t, and it is having a what you call amplitude of minus a. So this will be again for a bit period t, that is being carried out over here. So what will happen here to the what you call your x of t? X of t will be equal to, if we have logic 1 or binary 1, we will have x1 of t plus n of t. If we have 0 being transferred, we will have x2 of t plus n of t. Now, students, have you come across the line code technique? Something like unipolar signaling, bipolar signaling, and polar signaling. Have you studied that? All are sleeping?
No, ma'am.
Have you studied that line coding techniques?
Yes, ma'am.
Yes, ma'am.
Yeah. So now when I'm saying I am transmitting the information here, right? For binary 1 and binary 0, I'm giving plus a and minus a. So can you tell me what kind of signal I'm transferring, sorry, what kind of line code it has been converted to, or which type of signal it is? Unipolar or polar or bipolar? No, your voice is not clear. Yes, you can type it in chat box. Yes, please can you tell me which type of signal is that? I am saying I am having a and minus a. What it means? Is it polar? Or is it unipolar? And if it is polar, is it polar RZ or polar NRZ? Or if it is unipolar, whether it is unipolar Z or unipolar NRZ? Uh, so simply here when we are saying that we are transferring the information or the binary value 1, we are getting an amplitude of +1, and 0, we are getting an amplitude of -1. Simply we say that it is a polar NRZ kind of signal. Means for logic 0, say for example, this is your voltage level. This is your threshold value. Okay, that is 0. So in the polar sequence, what happens if 1 is transmitted? Okay, I have a sequence 1 0 1 1 0 1 1 and 0. If this is a sequence, then in a NRZ, I am saying NRZ means for the given clock period, I am not returning to 0 threshold value. Okay, say for example, these are my clock cycles. Just I want to tell you okay, what kind of input signal we are giving. There are various types of input signals which we can give to the receiver. Okay, so this is one clock period, this is another clock period, this third clock period, this is fourth clock period, right? So this is my clock. Okay, and this binary data in the form of pulses I have is 1. Okay, then I have 0. And I'll change the color here. I will change the color here. Wait. So this is 1, then 0, then again we have 1, and then 1 again, and then for the next clock cycle 0, right? Here this part you can erase because we have to take it as 1 only, right? This is our information, right? Now if it is a polar RZ form, because we are having plus A and minus A, so the signal is of polar NRZ form. So polar NRZ form means what kind of information is going. When it is binary 1, you are going to have, this is my threshold, okay, 0. So I'm not getting a straight line here. Okay, this is my 0 threshold. Threshold means what? A point at which, from which we can start conducting. Okay, so we are giving threshold here as 0. So in polar RZ, as per this one, we write as one means it will be, for the clock cycle, it will be plus A. Now 0 is there, right? This is 1, 0, 1, 1 and 0. So now minus A means it is for binary logic 0, you have minus A. Minus A means this 0 will come to negative voltage. Okay, so it is plus A here, amplitude, and here it is what? This is minus A. Okay, and then again next 1 1 it is, so 1 with a positive amplitude, another positive amplitude. Now it is 0 here, right? So this is basically for 0 we are getting a negative amplitude. So what kind of input signal we are giving here? It is input signal to the receiver. When we were coding at the, what you call, before entering into the channel, okay, the line code technique what we have used is the polar NRZ, that is non return to 0. Okay, and when I say the logic of 1 and 0, then we are talking about the what we call your binary phase shifting signal, BPSK signals. All right, I think you have already dealt with that. Fine. So basically just wanted to give you that we are considering here polar NRZ signal at the receiver end, which is given to the filter and finally sampled at every t second, and we get the output over here, right? This is what we have obtained. Now, since we have the binary 1 and 0, we are saying that plus A and minus A is being transmitted for that particular duration or for that particular value. We can simply say the voltage sampled at t interval or t second is given as x naught of 1. So this is for logic or binary signal or binary symbol 1, and this is for 0. Okay, when 1 is transmitted and when 0 is transmitted. So like this for everything, okay, for every part we are going to have its own associated noise. Now every bit is going to carry the noise. So what we are supposed to do? Accumulate all the noise and check, accumulate all the signals and check whether this noise can be made 0 or no, and if it can be made 0, how we can make it 0. And always remember that additive white Gaussian noise is going to have a 0 mean and the variance of n naught by 2. I think you have studied this. Okay. So optimum receiver, which is going to reduce, what you call, not reduce, which is going to have the minimum probability of error. Over here. Okay. Then correlated receiver. Correlated receiver, we have x of t. Yes, we are having some kind of dimensionality and some kind of basis function. You studied about dimensionality and basis function, students? Yes. Yes. What is dimensionality? The boundary or in the region where the values are going to lie, right? Say for example, you have like what is actually probability of error? In general way, I will say. Say I have some decision boundary. I am passing two message signals, fine, and that two message signals are having some region, fine. So say this is your region 1. And here you have region 2. Okay, I am passing the information as 1 and 0. Okay, and we see that in a normal signal, 1 was being traveled at, or 1 was supposed to lie in the boundary or in the region 1. Fine. And 0 is supposed to lie in the boundary or in the region 0, sorry, region 2. Fine. What happens when there is an error in the signal? Okay, when there is an error in the signal, we see that in place of 1 in the region 1, we may have 0. Okay, we may have 0, and in the place of 0, we may see that 1 may be transmitted. Okay, that is called as probability of error. Like this, you are having different types of techniques, modulation techniques, right? You have BPSK, FSK, then M array techniques, yes, QPSK techniques and all. And with respect to these, error passing, you are calculating the bit error rate and the probability of error rate. Yes. So here, this basis function, what we are talking, is with respect to the message signal and the region in which they are lying. Okay, and that is given to the integrator part, and finally they are vectored over here. Okay, so this input is again, these signals are again accumulated here at the collector end. Okay, you have a collector signal. Or the not collector, sorry, selector signal. You have a select signal here, and then whatever input you want, you can take it. So just wanted to tell about the bit error rate, probability of error. In which region, what information has to be passed. If that is not passed, in place of 1, 0 has gone, or in place of 0, 1 has gone, then we will call there is an error. And that probability of error we are going to calculate, or we are going to minimize. So to do that, we have a correlator receiver, which is using a modulator circuit and a integrator circuit. Okay, we have a modulator followed by an integrator. This is just for your reference, this correlator receiver circuit. Okay? You don't have much explanation related to that. The next is the matched filter. So here, now what is the matched filter? You see that an optimum filter, it is also one of the methods to demodulate the signal, which yields a maximum ratio of S by N. Okay, the signal to noise ratio should be high. Then we call it as a matched filter when the input noise is white noise. And the power spectral density of the input white noise is given by SNI of F in terms of frequency domain is given as N0 by 2. Okay. So now here we have to check the impulse response of the match filter and then say that the correlator filter what we are using or the match filter what we are using are having the same impulse responses. Fine. So first we will calculate the impulse response of the match filter. This portion I have extracted from your textbook itself so that it will be easy for you to understand when you refer it. So the impulse response h of t of a match filter can be obtained from the transfer function h of f. Okay, and we are going to use the expression for the transfer function of the optimum filter at the starting point. So the optimum filter what we have, its transfer function is given by kx conjugate of f divided by the, what is this, Sn of f. Here we have seen Sni of f is the power spectral density of the white noise given in frequency domain. Okay, into e raised to minus j 2 pi ft. Then for the match filter, the input noise n of t is assumed to be white noise. So therefore, what we will substitute? We will substitute that Ni of f is equal to N0 by 2. So when we substitute here Sn of f as N0 by 2, we get the transfer function value of an optimum filter as 2k x conjugate of f N0 into e raised to minus j 2 pi ft. Okay. Then next, what is the step? We see that what is the property of the Fourier transform? From the property of the Fourier transform, we see that x conjugate of f is means what? It is the reverse of the frequency, right? So x conjugate can be written as x of minus f. The same you are going to introduce in the equation 6.7.2, right? So when I do that, I get the transfer function as, the transfer function h of f as 2k n0 and x conjugate is replaced by x of minus f e raised to minus j 2 pi ft. And to obtain the impulse response, what we are going to do? We are going to take the inverse of h of f. And when we find out the inverse of h of f, we get h of t is equal to inverse Fourier transform of this particular expression. Okay, so this is how we are obtaining the impulse response of match filter. The impulse response of a match filter includes the power spectral density of the white noise. Okay, then when you take the inverse Fourier transform, what you obtain? The x of minus f becomes x of minus t, and the term e raised to minus j 2 pi ft is going to represent a time shift of t seconds. Okay, so simply you will write the Fourier transform of x of minus t is equal to x of minus f, and what will happen? There is a time shift. This particular expression, what we have, e raised to minus j 2 pi ft is going to have a time shift of t seconds. So we are going to have a time shift of t seconds. Yes. So the entire expression is written, or it is rewritten over here as h of t is equal to 2k by n naught, and that is equal to x of t minus t. Okay. But you know that the input signal x of t is given as what? x1 of t minus x2 of t. So now here we are saying 1 is transferred and here 0 is transferred. And both of them are going to travel at the same interval. Yes, same interval t. So don't get confused between capital T of this and capital T of this. Okay, same interval t, or t seconds you can consider here. So h of t is equal to 2k of n naught. For x1 of t, we are having a time shift represented signal, and here for 0 we have x2 of t minus 1. So these are the required expression for the impulse response of the match filter. So this match filter to this match filter, we are giving a polar NRZ signal. Okay, here we are giving a polar NRZ signal. So this signal is passing through this particular filter. Okay, we are having the Fourier transform and the inverse Fourier transform applications, and finally at the output end we are going to have this kind of information. Okay, impulses, this kind of impulses. Now the same expression is explained in your waveform. Okay, so the impulse response of the match filter, you can see, is a time reversed and delay version of the input signal. So my x1 of t is what? Positive, right? Here I had taken it. Where is that? I had explained logic 0, right? Polar form 1 के लिए पॉजिटिव एम्पलीट्यूड आएगा और 0 के लिए नेगेटिव एम्पलीट्यूड आएगा, राइट? ये वाला फॉर्मेट. ओके, so this is your input signal x1 of t, and this is your another input signal x2 of t. So this is your with respect to your negative amplitude. Yes, here these are the impulse response signals. Then finally the total output of the impulse response is given as this particular value, and it is a time reversed, right? This is the delayed version, time reversed and delayed version, correct? Then this entire information, again I'm going to reverse it. You can express either in this particular form. Here you are taking here as minus of t, right? Here as again minus of t. So when we shift it, okay, when we shift it, that is e raised to j 2 pi minus j 2 pi ft. When we shift it, we get a positive part, positive impulse. Okay, combining these two. So here we have the response of the match filter, that is x1 of t minus t and x2 of t minus t. Combined together, the amplitude is 2a here. Okay, 2a. So these are the waveforms. Now we are going to realize, okay, correlated realization of a match filter. Mean to say that the impulse response of this correlator, okay, and the impulse response of this match filter, we are going to say that they are similar. That is, h of t of correlator and h of t of match filter are equivalent. But when it is equivalent, how it is equivalent, that we will see now. So here you are giving a noisy input signal to a match filter, okay, and it is like, you know, filtering the information or calculating and then giving you certain output voltage for a over a time interval of t equal to TB. Okay. Just one second. Yes. So consider this block diagram. Okay, this is the block diagram for the match filter, and we are going to determine that the impulse response of the match filter and the correlate filter is same. So here, first you consider output of the match filter, which is given as V output of t is equal to f of t convolution with h of t. Okay, noisy input signal, we are considering it as f of t, and this match filter information we are considering as impulse, we are considering it as h of t. So V of t is a convolution part of f of t and h of t. Okay, then we know that the impulse response, few minutes back we have calculated the impulse response of the match filter. The impulse response of the match filter is given by h of t is equal to 2k by n naught into x of t minus 1. Now, when calculating the convolution of the f of t and h of t, which is given by this expression, means I have changed here equation 1, actually it should be 6.8.4 only. We can rewrite this as f of tau into h of t minus tau with respect to the convolution factor. So here what is h of t minus tau? Here the h of t minus tau, this particular information we are substituting here. We are substituting here. Okay. So this, when we substitute here, or you can simply say, we get this particular expression. What? This particular expression. Okay. Then substituting this value. Okay. Substituting this value where? In this particular expression. Substituting h of t minus tau in equation number 3. We get as V output is equal to integration of minus infinity to plus infinity f of tau into h of t minus tau is replaced by this expression. Okay. Then on further simplification, what happens? We are going to integrate. Integrate to what? To integrate over a given bit duration. Okay. And we know that the bit duration what we have taken is 0 to t. Right? So when we integrate and simplify this expression, we are going to come across at the output end of each bit duration, the output of the match filter is given by f of tau into impulse response, which is given as x of t minus t plus tau. So this t has changed to this t. Why? We are taking at a time interval, given time interval. Okay. And on simplification, what happens? This cancels out, right? And what is remaining? X of tau d tau. So we output at a given time interval. This is the instantaneous voltage, and this is the what? Sampled voltage at time interval t. 2k by n naught is again a constant value taken out. Then you have the noisy signal value and the input signal value. Okay, and we are going to substitute the tau value as equal to T here, and then you get finally the output of the correlator, and the match filter is same. Actually, you don't have the derivation for the correlator. Okay, you have only derivation for the match filter, and when we check the expression 8, okay, with the correlator expression, they tend to be similar. Okay, so we simply say the impulse response of the correlator and the match filter should be similar. Now coming to a conclusion, correlator and match filter are the two distinct techniques that yield same result. What is our end result? We want to convert our or identify our transmitted signal, identify the bits. Yes, recognize or observe the bits, whether they are correct or no. Yes, so for doing that, we have to filter the noise. To filter that noise, what we are using? Correlator filter and the match filter. So they are called as the synthesizing technique. Okay, so this correlator and match filter are used as a synthesizing techniques for optimum filter. Okay, then if you want to know what actually is the difference, both the match filter and the correlator filter, they maximize the pulse signal to noise ratio, the sampling instant in their output. Both of them maximizes the signal to noise ratio. Okay, they amplify the signal, they try to increase the signal by removing the errors or by removing the noise. Thus they are called as optimal receivers. Why? Because they are maximizing the SNR. Okay, pulses of the signal to noise, signal pulses they are maximizing, so that is why they are called as optimal receivers. Okay, then these two devices what we are seeing, this correlator and match filter, they are indeed different. Okay, how is their structure or how is their circuitry? Match filter is simply filter. Okay, but this correlator is actually a multiplier followed by an integrator. Okay, and if we look into the waveforms of the match filter or correlator, we see that their outputs are usually different from one another. But what happens at the best sampling instant, means at the best time interval, the SNR ratio of both the match filter and the correlator filter will be same. Okay, at a given instant when we are measuring, no, when we are measuring the signal to noise ratio at a given time interval or at a given rate, the signal to noise ratio of both match filter and correlator turns out to be same. So for that reason, we consider them as a what you call your optimal receivers. Okay, we are or optimal filters also you can say. See, when I'm saying filter, receiver, okay, the meaning is same. Optimal receiver is not different from optimum filter. Both are same only. Fine. So here we are any doubts you have here, you can ask. Any clarification? Students, if you have not understood the derivation part of your what you call impulse response match filter, you can ask me. It is just simply substitution. You need to remember the block diagram, and we are giving some kind of data sequence. Here we have considered a data sequence of polar NRZ form. Okay, or else it can be your what you call bipolar form also, or it can be unipolar form also. But the entire process remains the same. Only the waveform what we are going at is different. Okay, fine. So what I will do is I will share you one link in the chat box, right? You need to answer those questions. Fine. Yeah, please access that link answer the questions so that at least I will be satisfied whatever I have taught is conveyed to you. Maybe there is some confusions and like things will be there, but still I'm sure that I have delivered maximum part of information which will be helpful to you.
Okay. Hello, madam. Hello.
Yes, ma'am.
They have to submit it in 5 minutes, no? You have given time.
Yes, ma'am. They have to do it now only. I'll be sharing the results.
Okay, no problem. So meanwhile, madam, I request you to make your camera on just for because I want to take one screenshot on video.
Okay, ma'am.
Just a minute, madam.
I think students are.
Just 1 minute. Okay. Just 1 minute, madam. I am facing some problem for screenshot. I will take it once again.
Recording in progress.
Students,
Okay, solve it fast. Okay, is there any registration number? Some student has asked, madam, in the chat box. What is that?
That registration number means their university number or roll number, what they have, like students have displayed now your number SYB 5867 NTC.
Okay, okay.
So that when I send you the report, it will be easy for you.
Okay, okay. So you just do one thing, students. You write your division and roll number. Like if your roll number is 10 and division A, you can write SYA-10 so that it can be easily recognized.
Ma'am, only 2 students have responded so far. That is Avinash and Vinayak.
Okay, okay. So shall we wait for 5 minutes, madam? Or can you
Ma'am,
please? Huh?
I want all the students to reply.
Yes, yes. All of you have to reply for it.
One more time, I will share the link because I will discuss this answers now. Once you answer it now, see, it's 12:40. I'll give you 10 more minutes till 12:50. You answer me, then I will discuss those 5 questions, and then we will close the class for today's time. I mean, for today. Then tomorrow again we will meet with. We'll be dealing with the next part, that is your synchronization of the symbols, that is ISA, inter-symbol interference. As I told you that leaving the region, it goes to other region, you are calculating the probability of error. All those things we'll be dealing tomorrow. Morning when I started, everybody had raised the hand, right? Everybody were active. Now what's wrong? If you have not understood, tell me, I'll explain once again. You want me to share the information of the quiz? Please. Once again, I have shared in the chat box. Please click on the link and start submitting. See, these marks are just for my evaluation purpose. Okay. Just want to check how much information I have delivered to you. So please don't make it 0. Okay. Four respondents, 8, okay, 9. Fine, I want everybody to do it. Whether it is right, wrong, whatever it is, you just submit. Very simple and easy questions I have put. I have not put the equations also. Ma'am, even you can check it, ma'am.
Okay, okay, I will check, madam. I will check. Yes, it's very simple questions, madam.
Yeah, because just like थोड़ा सा बेसिक उनको दिमाग में रहेगा ना मैम, तो वो हो जाएगा उनके लिए. इक्वेशंस वो आराम से याद रख पाएंगे, इसीलिए ऐसे कुछ सेम किए.
Yes, yes, ma'am.
What happens, students? Shall I display the slides on the screen, students, so that it will be helpful for you people? Only 19 have responded so far. I want all the participants. What is the strength, ma'am?
Actually, the maximum students, whoever have joined, I will just check. It was around 115. So if we exclude both of us, 110 at least should be there. If some have joined double or what. 110 responses should be there. Please give responses fast. Only 5 questions are there. And
Only
some
10 minutes
students,
have
they are
given.
sending message. So registration number means you have to write simply your roll number and division, nothing else.
University number, and here there registration number, you simply enter roll number, students.
How many responses you got, madam?
Ma'am, 36 still on the count.
Okay, okay.
These students, we are not going to end the meeting until and unless all the 110 students submit the forms.
Okay, okay. Please send the responses fast.
Ma'am, 44 till now.
And those who have sent the responses, they have to be in the meeting only because madam is going to discuss about that. Don't leave the
Yes,
meeting
answers I will be discussing, ma'am.
till I am giving the instructions.
Yes, 57. Ma'am, only 62 responses, ma'am.
Okay, I have asked
Students
them.
last,
I have asked them to
last,
madam. Just wait. We will wait.
okay, ma'am. Last 1 minute, students. Last 1. Ma'am, time up. Shall we discuss, students?
Yes, yes, madam. Yes.
Yes, yes. Okay, I'll just share screen. So here 1 or 2 responses. See, okay, I'm really happy that the students have responded very properly.
So, how many responses, madam, you got?
You can see on my screen, ma'am. 1 or 3 responses are there.
Oh, okay, okay. Okay, good.
I'm happy, ma'am, because they have done it with 1 word.
Yes, yes.
All right. So here we go. So students, here in digital communication system, the signal produced by the source is converted into a digital signal which consists of ones and zeros. So to convert to ones and zeros, what do we need? We need is a source encoder. The source encoder is the correct answer here. Then coming to the next part. AWGN stands for additive white Gaussian noise. Correct? Yes. This was a very simple question. And then next, as I told you in the beginning, I had divided that receiver model, yes, into signal demodulator and detector, right? And then the optimum detector, we use an estimation theory for what? For designing a what you call our filter in such a way that we have less probability of error. Correct? We cannot minimize the amplitude. If we minimize the amplitude, the information will be lost. If we minimize the time interval, then what is going to what is going to happen? The bits can have the the bits can overlap, or we can see that there will be a long gap, because of which we may feel the signal is what do you call, there is miscommunication in the signal, like how our voice will break and all that way. So here we are talking about detection for minimizing the probability of error. Okay, and we cannot minimize the phase shift also, right? So if we minimize the phase shift, then again we are going to face the consequences. Okay, then in the integrated and the dumb filter, the voltage on the C at the beginning of each bit interval is what? 0. We need to discharge the capacitor. And how are we going to discharge the capacitor? By closing or by turning on the switch 1. Yes, that is there. Okay, the next one, correlator. So correlator, oh, I did not give answer for this. I'm so sorry. So correlator consists of what? Correlator consists of a multiplier followed by an integrator. Only filter is a match filter. Okay, and we not following any adder kind of what you call your symbol or addition. We are not adding up any signals and then we are going for selecting a signal. No, nowhere we are going this kind of process. We have various signals and then we select the signal, right? So the correct answer for this one is correlator consists of multiplier followed by the integrator, right? All right. Now I have 106 responses. I'll just download all the responses. And let's see who all have answered it. Okay. So here you can see the score, this particular block. Yes, you can see your scores. Patil Pratik has answered full. Vanita has scored out of out. Omkar, Yash, yes, and then Ganesh. If I have out any numbers, please don't mind. Then we have who Sonali and others also have tried to score. So okay, the score range is between 3 to 5, 3 to 4. I can consider. So on an average, like you were able to perform up to 70%. I can say 60 to 70%. Anyways, so we'll be there for the next session also for tomorrow. Yes, tomorrow we are going to meet at 9:30 and complete the remaining part. Tomorrow's part is slightly interesting because we have the symbols are overlapping, they are crossing each other. So how are we going to come out of that problem at the receiver end and deliver a proper information? If you have not understood anything from today's topic, sit and read once. In tomorrow's class, you can ask me the questions. Okay.
Okay, one request was there, madam. Hello.
Yes, ma'am. Yes, ma'am.
Can you please share your PPTs so that I can share it on group? If you don't mind.
Yes, ma'am.
Oh.
No, I will be sharing it, ma'am. Today is only I have prepared. I have not prepared completely. Shall I share it tomorrow or now only you want me to share?
Okay, okay. Tomorrow also you can share, no problem. Just for their reference, some students have requested. Okay.
Yes, ma'am. I'll be doing it. I'll be doing it, not a problem.
Okay.
Students remaining part I will add today and I will share it tomorrow.
Okay, okay. Okay, ma'am.
Okay, and ma'am, this feedback form also for the, not feedback, this quiz form for 1 and 2. Today's and tomorrow's also will be, and tomorrow we will have more questions, okay? Not 5, we'll be having more questions and time limit will be given for that.
Okay, okay.
All right.
Okay, no problem. Just last part. Students, you send your feedback related to session in the chat box. So please give your feedback in the chat box. I have to take the screenshot of that. Madam, can you please wait for 2 minutes? And
yes,
if you have,
I'm here only.
Okay. And if you have any doubts to ask, any questions to ask, time is there for that discussion. You can have discussion now. You can ask to madam if you have any doubt.
Yes, students, you can ask me if you have any clarifications from the part what I've taught.
Okay, please give your feedback in the chat box. I request the students. I need it for the some official documents. Give your feedback in the chat box about the lecture.
Ma'am, they are having like in the chat box they have options. No one host and co-host, everyone and everyone directly or anyone directly, something like that.
Okay, just 1 minute, madam. What you are saying, I am not able to hear. Can you please repeat?
No. When they are replying, they can everyone and anyone directly means what is happening is the students are chatting directly. I mean, they are messaging each other. That is possible. Can I change it to everyone? Participants can chat with everyone.
Yes.
I have changed it to that, ma'am.
Okay, madam. Okay.
Because directly also they can message you, ma'am. Now, like they will be able to message in the group itself.
Okay. Actually, within these 2 hours only, you have means done lot of interaction with them, madam, like a regular teacher. So I'm also very thankful to you for such an interactive session, because usually whatever are the guest lecturers, whatever is the usual expected thing, beyond that you have done, like creating the test for the students and all that things, madam. So I'm very thankful to you on behalf of our department as well as our institute. So again, tomorrow we will meet with the same enthusiasm, and I hope tomorrow students, tomorrow they will be more attentive, because they have to give one more test, and which will be having more number of questions. Okay. So thank you, madam.
Yes,
If students don't have any questions right now, later if they ask, I will communicate that to you. And for today, shall we stop here, madam?
Yeah, so much, ma'am, for giving this opportunity. And I hope students are replying that the session was nice. See, students, it happens like when it will be nice when you understand everything and you don't understand everything. Okay, but I expect you to come up with some questions so that I'll be able to, clarify that, and you get more insights on the subject what you are studying. Okay. I was really happy because everybody were active and attentive. There were no sleeping participants. Okay. And really, ma'am, thank you so much. You have coordinated so well, and your students also have given their 100% for this class. Your presence has motivated me to prepare much more better for tomorrow's class. Okay.
Yes,
Thank you so
yes.
much, ma'am.
Okay,
See you
thank
tomorrow,
you.
ma'am. Then.
Okay,
See you
thank you,
tomorrow.
madam.
Take care.
And thank you, students, for your active response. So tomorrow we will have a lecture at 9:30 in the morning. Okay, thank you. So shall I close, madam?
Yes, ma'am. Yes, ma'am. Yes.
Okay, thank you.